Okay, so welcome to linear algebra course. In today's class, we are going to review some of those concepts and then we are going to add some new concepts. So the first concept which I want to talk about is matrix factorization. So what does it mean? It means that we have a matrix and this matrix is given as say A, and we have to factor this matrix into a matrix B and C. Now please understand the reverse problem is easy to solve. So the reverse problem is, so what do I mean by reverse problem? Reverse problem is, if I give you a matrix C, if I give you a matrix B, and if I ask you multiply these two matrices, and please note matrix multiplication is commutative, so you have to maintain this order, you can get me the matrix A. However, the reverse problem is not very easy to solve. And there are important factorizations, there are important ways you can divide or separate or partition this matrix. And some important factorizations are first, which is called as LU factorization. So you replace A as a product of L times U, where L is a lower triangular matrix multiplied by an upper triangular matrix. And it may be difficult to visualize or understand why these factorizations are needed. But please understand factorizations are very important for understanding numerical linear algebra. Factorization allow us to perform computations extremely quickly. They also give us important geometric interpretations, and it gives you a very physical basis for understanding the equations and the math. So we will talk about these, but please understand this LU factorization is achieved using something called as elimination. Then another next important factorization, but I just need to explain what this lower triangular means. The lower triangular means that you have terms here. So there are numbers here, and the upper triangular is 0. The upper triangular matrix means just the opposite. Here are all zeros and here are all entries. So diagonal is, there is some entry here. So something like this. So you have an lower triangular matrix and you have an upper triangular matrix. The next important factorization, there are actually 5 important factorization, but let's start with a simple factorization. Next factorization is a matrix A that is represented as Q times R, where Q is an orthogonal matrix. So this is an orthogonal matrix multiplied by an upper triangular matrix. And this is the classic Gram-Schmidt technique. And we will talk about it. But what that means is each column or each row of this matrix is perpendicular to each other. One classic example of an orthogonal matrix is 1 0 0 0 1 0 0 0 1. So if you take any row and multiply that with any column. So for an example, if I take this column and then multiply this with this column, I get 0. So 1, 0, 0 multiplied by 0, 0, 1. This is actually called as the dot product. This dot product is 0. This is called as the dot product. So anytime if I ask you to take the dot product of two vectors x1, x2, then the dot product usually is x transpose x3, or uh, so basically um, you need to transpose one vector and then multiply with the other vector. Now let me take one more example for clarity. Now if I have this vector, I'm going to call this vector y1 and I'm going to call this vector y3. So please understand, x1 and x3 are column vectors, and y1 and y3 are row vectors. So now what I want to do is I want to take a dot product of y1 and y3. If I want to take the dot product of y1 and y3, what you need to do is dot product is a scalar product, which means at the end we are gonna get just one number. So y1, if you think about it, is one row, three columns. Y2, y3 is also one row, three column. The only way that this product will give you one, please understand, y1 cannot be multiplied with y3, because please note, for matrix multiplication the dimensions should match. So for an example, this dimension and this dimension should be same. Since it is 1 times 3, that this matrix multiplication is not possible. So what I need to do is I need to do y1 times y3 transpose, and when that happens, I have 1 times 3, 3 times 1, these two numbers match, and finally I get 1 times 1. So this is the dot product. So if I take the dot product, I need to have a y1, which is 1, 0, 0, must be transposed with 0, 0, 1. And then the resultant is 1 times 0 plus 0 times 0 plus 0 times 1. So the dot product of these two vectors is 0. So whether you take a column vector or whether you take a row vector and multiply that with any other column or any other row, you are gonna get 0. Now this would be a very important observation. Why is this called as a dot product? Now please understand, classic definition of dot product is we have a vector A, we have a vector B, we have a vector A, we have a vector B, A dot B. So please note, A and B are vectors. A dot B is the magnitude of A multiplied by the magnitude of B multiplied by the cosine of angle in between these two vectors. So cosine of theta. And what I want to do is I want to take a minute just to explain what the dot product means in the concept of vectors. So imagine I have this plane and I'm gonna express x here, y here, and I'm gonna express z over here. Now this is called as R3. Why it is called R3? Because you have a dimension R, you have another dimension R, you have another dimension R. So the space occupied by these three perpendicular vectors is a three-dimensional space. So what I'm going to do is I'm going to draw the first vector. So I'm going to take this vector y1. This is my vector y1. Y1 is 0, 1. So I will draw this vector, and then actually this is my vector y1. Now I'm going to take the second vector, which is y3. And please understand, this vector y3 is 0, 0, 1, which means 0. So this is starting from 0. This is 0, 0, 0. This is the origin. And this is going to become the vector y3. Now please understand, these two vectors are perpendicular to each other. So if I were to find out the dot product of these two vectors, magnitude of vector y1 is 1. Please note, magnitude of vector y1 is 1, magnitude of vector y3 is 1, and the cosine of 90 degrees, then this gives me a 0. So basically, a vector multiplication is same as a dot product. So this is also called as, and this is very important, inner product. This is called as the inner product. Now, the last important factorization, which we will use quite a bit, is something called as uh, factorization of a matrix A into something called as a left singular vectors, singular values, and the right singular vectors transpose. So this is completely given by, you have an orthogonal matrix, ortho matrix, then you have a diagonal matrix, and then you have an orthogonal matrix. And this is also called as singular value decomposition. And this is the most important concept in the linear algebra. This is the basis for the PageRank algorithm that Google uses. This is the basis for the machine learning algorithms that are used. And this is the basis for lot and lot of AI type applications, vision, signal processing. So I would strongly recommend that this is the transformation that uh, you should be extremely comfortable with. Now, we will spend at least 1 or 2 lessons or possibly more on singular value decomposition. But what I want to do is I want to tell you here that A does not have to be square. It could be a rectangular matrix, and the rectangular matrix could have a singular value decomposition. Now, at this point, I want to explain one more concept. Please understand that this matrix shown over here, this is the matrix that we have over here. This is actually an identity matrix. This identity matrix, so this identity matrix I has 3 columns, x1, x2, and x3. This is called as the column space of the matrix. This is called as the column space. The same matrix has something called as y1, y2, and y3. So x1, x2, x3 is the column space. y1, y2, and y3 is called as the row space. And these matrix decomposition, they are inherently related to this column space and row space uh, formulation. For an example, U, R, and V are the input bases based on column space fact nomenclature, and L, Q, and U are output bases based on the row space factorization or row space uh, indication. And please note, these three factorizations that we talked about. So first is A into LU, A into QR, and the last one is A into U sigma V transpose. They are inherently related to the column space representation and the row space representation of the matrix. And we are going to spend a lot of time about talking about how to decompose and how to find out different decompositions and how can we use those. So what I'm going to do is I'm going to quickly talk about the concepts that were discussed in the videos, but I will try to give you some theoretical basis. So the first concept which I'm going to talk about is the linear combination of vectors. So can someone tell me, based on the video, what do we mean or what do we understand by linear combination? Any comment?
Combinations of all vectors with
Okay. So imagine you have a vector V which has three components, V1, V2, and V3. Okay, this has three components. And what we want to do is this vector can be represented in a three-dimensional space. So this vector can be represented in three-dimensional space. So if I were to say this vector V is given as 2, 4, 1, I can physically draw this vector in this three-dimensional space. Please note, this is R3. So this is R1, a line is R1, plane is R2, and the three-dimensional space is R3. So I can actually go in X direction. So I'm going to call this 2, X direction. I can go up in Y direction 4. So this is 2, this is 4, and I can go ahead here in 1. And then what I can do is I should be able to construct some sort of an imaginary rectangle that is representing this. And then if I were to draw a line and then point an arrow, this is my vector V. It is very important that this vector V has three subcomponents, and these three subcomponents are independent of each other. What it means is a vector in R1 cannot be expressed as a combination of R2 and R3. So let me talk about what we mean by a vector combination. Say for an example, if we have a, a vector, something like 1, 0, 0, and if I have another vector 0, 1, 0, and now I have another vector 2, 5, 0. So, and I form this matrix. So this is my matrix A. Now please understand, if I want to use the same logic, I can say this is my x1, this is my x2, and this is my x3. And it can be seen very clearly that if I multiply 2 times x1 plus 5 times x2, I get 2, 5, 0. What that means is x3 can be represented as 2 times x1 plus 5 times x2. So x3 can be represented as 2 times x1 plus 5 times x2. Now let's try to visualize what does this mean in this space that we have seen as R3. So what I'm going to do is, this is again my R1, this is again my R2, and this is again my R3. So if you want to think about that, this is the x coordinate, y coordinate, z coordinate. So in x, I have this 1. So this is my first vector. I'm going to call this x1. Now my second vector is y. So this is going to be my second vector y. So let me draw this over here. I'm sorry, x2. This is my x1. This is my x2. This is my x2. And now what I want to do is, I want to plot this vector x3. And please understand, x3 is 2, 5. So x3 is basically 2, 5. My x1 is 1, 0, 0. My x2 is 0, 1, 0. And my last but not least vector is 2, 5, 0. Now, have you noticed that this final vector is in this plane? So this final vector that we are talking about is in this plane, which is comprising of R1 and R2. So this is my vector. Now, even though I have R3, there is nothing in R3. That means even though I have this matrix represented something like this, the last column vector, which is column vector x3, is expressed as some component of x1 plus some component of x2, which means that my final vector x3 can be resolved. Please understand, finally, this is a vector. This vector x3 can be resolved using the vectors in R1 and R2. What that means is the last, the rank of this matrix, the number of independent columns or independent rows, the rank of the matrix, and rank is the subspace number of, so whether we need, if I just have R1, that means the matrix rank is 1. If I have R1 and R2, that means matrix rank is 2. If I have R1, R2, and R3, that means the matrix rank is 3. So based on what I'm seeing here, rank of the matrix is 2. because all the vectors in the row space or in the column space can be expressed only using the two basis vectors. Everyone understood this? So this is what is called as a basis representation. The other way to say that is vector x3 is dependent on x1 and x2. What other way to say that is vector x3, x1 and x2, they are in R2 space. So that is where all the vectors can be represented. Everyone understood this? Any conceptual questions here? Now, this question of dependence and independence is going to be super important when we look at how do we solve equations. But before we do that, what I want to do is I want to show you a matrix vector multiplication. So the second concept which I want to talk about is matrix and vector multiplication. And so if you look at the undergraduate linear algebra, this is how we perform the matrix multiplication. So if I have a matrix 2, 5, 3, 7 multiplied by V1, V2, the way to do this is 2V1 plus 5V2 and 3V1 plus 7V2. This is called as the row way of multiplication. So basically, this is how we multiply. Now, please understand there is a column way of multiplication as well. And I want you to notice this is 2, 3, 5, 7 multiplied by V1, V2. Now, the way we would assume this is, please notice, this is a vector. So I'm going to call this vector x1. This is another vector. I'm going to call this x2. And V1 and V2 are the weights to these vectors. So I can say V1, 2, 3 plus V2, 5, 7. This is going to give me 2 V1, 3 V1 plus 5 V2, 7 V2, and that yields 2 V1 plus 5 V2, 3 V1 plus 7 V2. So the result is the same, but interpretation is slightly different. So how do we interpret this? This is called as the column way of multiplication. So what do we mean by column way of multiplication? Now please try to understand row way of multiplication you have done as an undergrad. Now let's try to visualize these two vectors and see what it means. So first, again, I have an R2 space. So basically this is my R1 and this is my R2. So I'm going to represent my first vector 2, comma 3. So this is my 2, this is my 3. 2, 3. So this is my first vector. This is vector x1. Next vector is 5, comma 7. So 5 goes here and 7 may be somewhere over here. So bear with me, 5, comma 7. So this is the second vector, 5, comma 7. Now, if you remember from the previous logic, the resultant of the vector, which is shown over here, the resultant of this vector here is nothing but it is multiplied, and the space, if you were to say 2 comma v1 plus 5 comma v2 and 3 comma v1 plus 7 comma v2, it is important to observe that that vector is going to be somewhere in this space. So this would be the space which is basically formed by these two basis vectors. So these two basis vectors, they will enclose this resultant vector. So this resultant is nothing but the algebraic sum of these two basis vectors. And again, x1 and x2 is called as the column space. So column space indicates the basis vector of uh, the multiplication. Now we talked about the matrix vector multiplication. Now what I want to do is I want to extend this further to perform matrix multiplication. And the reason I'm trying to show you these different ways of multiplications is the interpretations are different. So let's start with the classic matrix multiplication, which is again row type of operation, row times column. So I have a vector, I have a matrix, sorry, 1, 2, 3, 4. The next one is 5, 7, 6, 8. And we know first row, first column. So 1 times 5 plus 2 times 6, then 1 times 7 plus 8 times 2, 3 times 5 plus 4 times 6, and 3 times 7 plus 4 times 8. Remember, this is how we learned in undergraduate linear algebra to perform matrix multiplication. Now, the other approach is what you can do is you can take the matrix A and multiply that by columns of B. Now, what does that mean? And I will not perform the whole multiplication, but I will show the multiplication once. So you can extend that to 1, 2, 3, 4. Then again, I have 5, 6, 7, 8. And this multiplication is going to be written as, so I'm just gonna draw the first, this is 17, this is 39, And here is another number. Here is another number. This is because 5 multiplied by first column vector plus 6 multiplied by second column vector, that gives you the column vector 1739. You can extend the same thing for this guy here. Again, your basis vectors are going to remain the same, 1, 3, and 2 and 4. However, your weights are going to be different. In the first case, you have 5 and 7. So in the first case, you have 5 and 7. In the second case, you are going to have 6 plus 8. And whatever product that you get is going to go 5 times whatever you do here. So let me just be very careful here. So first your weights were these. These were the weights for the first multiplication. And for second multiplication, these are going to be the weights. So it will be 7 and 8. And please understand, if you look at the answer, at the end of the day, the answer is going to be the same. Third way of multiplying this matrix is row of A and matrix B. So row of A and matrix B. So let's try this again. You have 1, 2, 3, 4. Then you have 5, 7, 6, 8. And now I'm going to perform this multiplication slightly different way. So 17, 23. There are again two numbers here because I'm gonna say 1, 5, and 7. So what I have used here is I have used the row vector of uh, the second plus 2, 6, 8, and now observe that I get 17, 23. And clearly for the next step, what I need to do is uh, I have to use the exact same logic 5, 7, 6, 8, and now I would have 3, 5, 7, and 4. Here it will be 4, 6, 8. So please understand here this goes here and this goes here. So again, the answers are going to be the same. The fourth way of multiplying matrix times matrix is column of A and row of B. So the way this can be done is if you look at 1, 3. So this is the first column. Multiply that with the row of B, 5 times 7. You are gonna get one matrix. First row, first column, 5 times 7. Second row, first column, which is 15, 21. And then what you're going to do is you would have 2, 4, and 6 and 8. So 2, 4, and 6, 8. And then you are going to have 12, 16, 24, and 32. And then essentially you would add these two matrices. And when you add these two matrices, 5 plus 12 becomes 17, 24 plus 15 becomes 39, 16 plus 7 becomes 23, and 21 plus 32 becomes 53. So these are 4 different ways you can actually perform a matrix multiplication. A quick recap: row times column is what you studied in undergraduate linear algebra. Matrix times column is using the basis vectors. Row times matrix, again you are using the basis vectors, but here you are using column vectors. So first, I mean, here you are using the row vectors. So let me write that row vector. This is you are using column vector. And here you just flip row times column to columns times row, and still we got the exact same answer. Any questions here? Because these interpretations are super important as we actually go deep into understanding factorizations. Now, one thing I want to talk about is an important factorization that is unfortunately not discussed, is something called as column times row factorization. So, and this is called as a CR factorization. A is equal to CR. So this is matrix A factored into columns and rows. Now, let me try to show you what this transformation is. So if you think about it, uh, let me pose a reverse problem. I have a C times R and I want to formulate A. So I'm going to say my C is 1, 2, and maybe 3, 4, 5, 6. Okay. So these are my columns. This is my first column vector, which is x1. This is my second column vector, x2. This is my third column vector, x3. And my rows, so I'm going to say my rows are maybe 1, 2, 3. And maybe I can say the multiplication of these two is going to be 1 multiplied by 1, 2 plus 2 multiplied by 3, 4 plus 4, 3 multiplied by 5, 6. So this gives me something like 1, 2, plus 3, 4, 5, 6. So this will give me 1, 2 plus 6 plus 8 plus 15 plus 18. So I actually did the multiplication something like this, and I found a vector. Now, this vector is, as you can see, I have 3 rows. So sorry, 2 rows, 3 column multiplied by 1 row. I have two rows. I have 3 column, and I have 1 row, 3 columns. So these independently become weights on these. Now I can do the reverse. I can do the reverse. So what I can do is I can take a matrix A and I can represent that as a representation of the column vectors multiplied by the row weights. So I would write this A, and let me take a most general matrix M times N. If I were to represent that as a column matrix and a row matrix, I can write this as M times R times N, and this would give me my final matrix uh, M times N. So I have, this is called as the factorization of the matrix A into the row space and the column space. So this is column times row factorization. Now, column times row factorization is very, very important because it gives us an insight on what basis vectors comprise this matrix. Now, let me give you an example. Imagine that you have a face, okay, and you take a picture. This image is actually, if it's a black and white image, it's actually a matrix that has the size M times N. And what I want to do is, I want to find out that what are the most dominant features of this image. For an example, the most dominant feature is like a circle. Then the next dominant feature is like the body. Then next another dominant feature is like hands, and then legs. So if I were to look at the most dominant features of this image, and then what I can do is I can combine these subsets together, that gives me the final image. So basically, if I were to take this image can be factored into its subcomponents. These subcomponents can be weighted. So for an example, if someone's, you have not only one face, but you have maybe 10 faces, what you can do is you can find out the most common features in each and every image and represent that as something called as the basis image. And this is also something called as the eigen faces. Eigen faces. And represent that image as weighted combinations of the basis images. And that is super important when we try to find out the patterns in the data, when we try to find out various features in the data, when we are trying to find out how we can compress the image. So that information is encoded in the basis vectors of the image. The other important concept that this factorization C times R factorization yields is, believe it or not, this factorization is the basis of the factorization, which is L times U factorization, which is you have a lower triangular matrix and you have an upper triangular matrix. This factorization can be represented as another classic factorization, which is Q times R factorization. And another important factorization that is seen is if your matrix is symmetric, this symmetric matrix can be represented as an orthonormal matrix, a diagonal matrix, and the transpose of an orthonormal matrix. So this is an ortho matrix. This is a diagonal matrix. And this is the transpose of ortho matrix. Now, one thing, I want to take a very simple example, and I want to take this matrix. This matrix is 0, 0, 0, 1, 3, 4, 2, 6, 8. And if I were to express this matrix and something like this, 0, 1, 2 multiplied by 1, 3, 4. First and foremost, basically, uh, there is a question from Shubha, like how did I multiply these matrices? So basically, this is not a strictly matrix multiplication, even though I wrote it like this. These are the actual weights that are multiplying the each column vector. So what I wanted to tell you, or I should have explained it a little bit better, x2 and x3. So you have these basis vectors x1, x2, and x3, and these are the respective weights on those basis vectors. So the resultant vector is the linear combination of x1, x2, x3. So this is not a strict matrix multiplication. So this is not a strict matrix multiplication, because please understand, this matrix multiplication cannot happen. So you cannot have 3 times 2. What I wanted to convey here is these are the weights onto these basis vectors. I hope that clarifies. But what I'm going to show here as the second example is, if you look at this, this is 3 rows, 1 column, 1 row, 3 columns. Now I can perform a matrix multiplication on these two and get the matrix. So if I were to do first row, first column, I get 0. First row, second column, I get 0. First row, third column, I get 0. Second row, first column, I get 1. Second row, second column, I get 3. Second row, third column, I get 4. Third row, first column, I get 2. Third row, second column, I get 6. And third row, third column, I get 8. So please understand, what I have done is I have this matrix A. This matrix A was represented as one column and one row. And one thing that I want to tell you is this matrix, and I would encourage you to try doing this in MATLAB. And let me make this absolutely clear. So what I wanted to show here was, if you look at this matrix, this is again the column vector weighted by those independent bases. So if you look at the way this matrix multiplication got carried out is like this column vector. So 1 times the column vector. This is 3 times the column vector, and the last one is 4 times the column vector. Now, looking at this, my question to you is very simple. My question is, what is the rank of this matrix based on the math that I showed you? What is the rank of this matrix? And if you have MATLAB, I would strongly encourage you to try this. Otherwise, if you don't have MATLAB, I want you to understand this first column is 0. Uh, First row is 0. Second row is 1. And third row is 2 times the second row. So basically y1, y2, and y3 is y1 is 0, y3 is equal to 2 times y2, which means the only independent column in this entire matrix is 1. So basically the rank is equal to 1. Now, since the rank of this matrix is 1, it is extremely important to understand that I have a column vector, I have a row vector, and its rank is also 1. Now, what does this mean? It means if, so let me write this down. If matrix A has rank 1, it can be represented as one column vector multiplied by one row vector. And one column, one row is rank 1. If matrix has rank is equal to 2, then it can be represented as combinations of two rank 1 matrices. So this is one column, one row. So this would be a matrix with one rank, and you will need one column, one row. This is rank 1. So as the keynote or note something to observe is, if the matrix A has rank 2, it can be represented as two rank 1 matrices. So the takeaway from here is rank n matrix, rank n matrix can be represented as n rank 1 matrices. And once again, I will repeat this. So if you have a matrix and that matrix has rank n, that can be represented as n rank 1 matrices. And I will give you a very trivial example. Imagine a matrix, identity matrix 0, 0, 0, 0, 1, 0, 0, 0, 1. This matrix can be represented as 3 rank 1 matrices. This is one matrix 0, 0, 0, 0, 1, 0, 0, 0, 0 plus 0, 0, 0, 0, 0, 0, 0, 0, 1. Now, takeaway here at this matrix has rank 3. This rank 3 matrix is represented by addition of 3 rank 1 matrix. Everyone understood this? Any question here? Now, fact of the matter is, for this type of decomposition, the matrix doesn't have to be square. If we have a rectangular matrix, we can actually convert that into its multiply that with the transpose and convert it into something called as the symmetric matrix. And if you have a symmetric matrix, then the most important property of the symmetric matrix is that all the eigenvectors are orthogonal to each other. Now, what I want to do is, I want to take the same example and explain this with the identity matrix that we have. What do I mean by the symmetric matrix? Symmetric matrix means all the off diagonal terms are same. So as you can see, and then the last term is this. So what I have here is, I have a symmetric matrix. If I were to find out the basis vectors or eigenvectors of symmetric matrix, are perpendicular to each other. And this is a very important property. And we will use this again and again and again and again in future. And clearly you must have seen the videos. So that brings me to my next question, the concept of eigenvalues and eigenvectors. So what are the eigenvalues and what are the eigenvectors? So I will give you a quick recap. So if we have a matrix, say 1, 2, 3, and 4. Okay, if I have a matrix and I multiply that by any vector, say 1, 1, what happens is I get maybe 4 here and I get maybe 6 here. So this vector get transformed, this vector 1 gets transformed to vector 2. The only problem is, if you were to look at the vector 1 and vector 2, if you look at the vector 1 and vector 2, they may not be collinear. So what it means by something like this, let me draw these two vectors. So first vector is 1 comma 1, so this is 1 comma 1, and the second vector that I get here is 4 comma 6. So this is my first vector, this is my vector v1, and my second vector is 4 comma 6, 4 comma 6. So this is my vector v2. Please understand, vector v1 and vector v2 are not collinear. v1 and v2 are not collinear. But there is a specific vector. So there is a specific vector. That vector, if you multiply by this matrix, will give you another vector that would lie on the same line that of previous vector. So again, imagine if this would have been an eigenvector. So 1, 3, 2, and 4 multiplied by the eigenvector. If it would have been an eigenvector, let me quickly find out what is the eigenvector, and I will show you that to you in just a second. A is equal to, I'm using MATLAB. So because this is super important. So if I use the vector something like 0 and 5.37, no, sorry, I use the vector something like 0.9 and 0.4. If I use this vector, this is a special vector. This is a special vector. And if I perform this multiplication, that is going to give me 0.9 plus 1.2, and then 1.8 plus 1.6, and this gives me 0.9 plus 1.2, which is 2.1, and 1.8 plus 1.6 is 3.4. So if you look at first row, let me see if I did this correctly. First row, first column, and second row, first column. And now if I were to plot this, oh, this has a negative sign. I made a mistake. A negative sign. So this is going to become 0.3 and minus 0.2. So what I want you to understand is 0.9, 0.2, this is 0.9, 1.1. If I were to plot these here, this is minus 0.9, so this will be somewhere here, and 0.4, which is somewhere here, So if I were to plot, and again, since I have a negative term, I need to write this down. This is minus 0.9 and zero point 0.4. This is 0.9, 0.4, and my vector is going to be something like this. And if I look at the second vector, which is 0.3, uh, which is going to be somewhere here, and minus zero point 0.2 going to be somewhere here. If I were to draw the second vector, please note that these two vectors are collinear. So this guy is here and this guy is over here. And that's what it means by having an eigenvector. So the eigenvector means it's a special vector that when we multiply this special vector by that matrix, we get another vector which is a scaled version of the same vector along the same line. And again, for this matrix, there are two eigenvectors, and eigenvectors are scaled by the eigenvalues. So if you look at this eigenvector, the scaling factor between the original vector and the modified vector is nothing but you get the relationship between the eigenvalue. And we will discuss this in a little bit more detail when we talk about eigenvalues and eigenvectors and its application in next class. So I'm going to stop here, but at this point, if there are any questions on the material that we discussed so far. Any questions on the material that we discussed so far? I will upload the video and I will upload the slides to Canvas,
Sir,
and, and I will have one more assignment for you to watch. So now I want you to watch the advanced videos on the factorization. So I will add the link. Okay, question. Yes.
sir, at last you took an separate matrix for eigenvalues and eigenvalues, right? Like you calculate the eigenvalues like 1324 is a matrix which gives us the I did in the MATLAB like eigenvectors, and I'll get a diagonal matrix like minus 0.9 and 0.4. That is what I got. But 0.3 and minus 0.2 is another matrix. Which how did you take that matrix actually?
Okay. Very good question. I should have shown this. Can you see my screen?
Yeah, yeah, sir. Sure, 100%.
So this is the matrix 1324. Can you see that when I find out m times n EIGA, I get this
You,
matrix,
yeah, sir.
wherein 0.9094 and 0.4160, this is my first
First,
eigenvector.
yeah, yeah, sir.
And then this is the second eigenvector. And what you see here is these are the eigenvalues of the
Values.
matrix. Now, uh, it is very important to understand the geometric interpretation. So in next class, what I'm going to do is I'm going to do some MATLAB activity where we will try to plot these vectors. So there is a command called quiver, and you can use that command quiver to plot the eigenvectors. And I think that will give us a very detailed understanding of how these transformations are taking place. Okay, but this is the command that I used, and these are the vectors that I got.
Yeah, sir. Hello.
Yeah.
Yeah, sir. That vector you got, but the thing is, like at last you had a vector minus 0.3 and 0.2. How did you take that vector?
Oh, basically what I did is I used this eigenvector and multiplied that eigenvector by
O-
the matrix. So what I
Okay.
did,
Yeah,
okay,
I got it, sir. I got it. I
so
got it right now.
basically,
Yeah,
so
you multiplied the first column of the eigenvector and eigenvector with the A matrix. So you'll get
then
the
multi.
values minus 0.3 and minus 0.2. That is right.
This is what I did.
Yeah, sir.
Oh,
Yeah, sir. I understood.
I need
I
to do
got
the
it.
transpose. So I have this matrix A and I have this matrix M. So I actually took this matrix and then I got this result.
Yeah, sir.
And then I actually plotted that. But there
Okay.
is a possibility that I might have made the mistake in the calculation, but so please check. But at the end, what's going to happen is if you multiply a matrix by the eigenvector, then the new vector is on the same line as the old eigenvector. That's what it is. Okay, I'm gonna stop recording, but I would encourage you to rework the math, uh, doing math and showing it on MATLAB during runtime. It's always possible for me to make mistakes, but please check this. And if you have any questions, let me know. Thank you.